Okay, so for the answer for number one, you're just finding slope. That's all you're doing. F2 minus F0 over 2 minus 0. And remember, function is 4x, root 4x plus 1. So just plug in the values for x, right? Not that hard. Find the slope. Do likewise between 10 and 12. So that's okay, number one. Pretty straightforward. Number two was asking what? Estimate the slopes of the secants for those various points. Great, just do that. And explain in words what it means in the context of the situation. And estimate the speed of the car at point P, which is be the tangent line, or the instantaneous rate of change, by the way. So you get 42.5, 45.83. We're working our way closer and closer to 50. So it looks like it's going to converge at 50, right? That makes sense. Now, what does it represent? Now, remember, slope is a change in y over change in x. What's my y value? Distance, right? What's my x value? Time. So you're looking at change of distance over time, or hence speed, right? And it's average speed because it's an average rate of change. So that makes sense of the context, the linear motion that's happening here. We're good. Okay. And approximately 50 meters per second at point P. For number three, that should be pretty straightforward. Use that expression that we talked about to find the slope of the curve. So we talked about how to do that analytically. You just got to plug in. Oh, that's a different one. I didn't show you that formula. How are you guys with that one? Are you guys okay, three? Yeah, sorry. I didn't. That's the alternative definition. It's very similar to f of a plus h minus f of a. Fx is a general function. F of a is, of course, evaluated at whatever a value is, which is 1 in this case. Work it out nicely. You should get that. So then plug in 1 to get 2. So this means that the slope at x equals 1 is going to be 2 at x squared plus 4. If I were to plot that, it would look kind of like this, I think. You have a point at what, 1 comma 5? If I found the slope of that line, geez. Found the slope of that line, that should be about 2. So, yep, that's what's happening for number 3. For number 4, he said use the limit definition of the slope. Okay, so you just got to go through the motions there and work it out. And again, I'll share these solutions with you guys later today. I'll put it in Schoology, and also I'll try to print them and have it ready by tomorrow. That makes sense. What's happening there? Because you're valuing at -1, right? You got to do -1 plus h minus f of -1. Do all the algebra, clean it up. You should get the h's canceling. You should get 2 minus h, plug in 0 for h. You get 2. And for the next one, root x minus 2, do that. You should get 1/4. And you got to do the conjugate to kind of help you out there with that one. So we're okay with that too? Yeah, cool. All right. Good. How long did the homework take, by the way, roughly? 30 minutes, 40 minutes? Okay, that's fair. I'm good with that. 6, a bunch of things to do. Use that to find an expression for that derivative or that slope of the curve. Then find the slope, use the slope expression part to determine the values of x equals that gives it. Yeah, you want to solve with -1/9. So once you actually solve it, set equal to -1/9 and solve it, that you guys could be fine with. 2 different answers you get. And then for C, it says do the graph and mark the tangent lines. And then what happens if A is approaching plus or minus infinity? Well, obviously it's going towards 0, right? So we know that. That's not hard. So we're okay with that too? Yep. Okay. For 6, so that was 6. Oh, finally the last one. Wait, that was dumb. That's with number 7. The average rate of change is represented by the slope between 2 points on a curve. The instantaneous rate of change, I didn't really use that term too much, but I think I talked about last time, is simply the slope of the curve or the slope of the tangent line at that as for some point on the curve, which we call the derivative. So, okay, we're good. Okay, ready to pass on to the next thing. Good, perfect. Let's do the next thing then. So I think I have the notes. Okay, it's going to take me another 5 minutes to get to the right folder. I'm just kidding. I don't know what's going on today. Here we go. Lecture notes. All right. You guys excited for March Madness? No, kind of not really. Okay. I'm just excited to see UC San Diego play.
Yeah.
So first time ever.
Ever.
Was that?
Yeah, Michigan, right?
They play Michigan. Well, it's close. It's a only 2 point favor. Hold on, let me. I don't know. 'Cause- 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 For a 5-12 matchup, it's a pretty close spread.
First time they've ever played.
UC San Diego, they have never.
Oh wow.
They were D3 when I went to school there 20 years ago. So it's pretty exciting. But if they lose, I just default to my wife went to U of A in Kentucky. I just default to those schools. Stanford's not
Let's think of
either.
SDSU. The CSU played. They went pretty far.
A couple years ago, I think, right? If I recall it correct, or 3 years ago. Okay. Let's move on to page 7 of these notes. Or sorry, that doesn't make any sense to you guys. Just 3.1. Here we go. All right. Pace myself so that I do this appropriately. Okay. So we got quite a bit to do, but we'll get through it. Okay, the slope of the curve. We know this, right? From the last section. F of A plus H minus F A over H. Limit as H approaches 0. That's the slope of the curve. We also call this the derivative of F at X equals A. So derivative is the same exact thing as the slope of the curve. We also call it the instantaneous rate of change because you're looking at that particular moment, at that instant, how Y is changing with X for that curve. Whatever that curve is modeling, whatever it's representing, the slope of that curve at that point is what we're interested in. Remember the average rate of change, we know is this. If I just write it again, you guys know this already. It's simply F of A plus H minus F of A all over H. Just that on its own is, oh, bless you. That on its own is the average rate of change. Okay, if I copy that again by one slight wrinkle, but it's a very important wrinkle, what would I add to the left of it to make an instantaneous rate of change? You add a limit. So subtle but very important difference. By putting that limit, now I'm indicating that, wait, I want H to be 0. So I better want, these 2 points must be the same. P and Q must be the same. So that's going to, instead of passing 2 points, only pass to 1 point, that's a tangent line. And that's at that moment, at point P, what is the slope there, right? That's what we're trying to figure out. Okay, does that make sense? From a theoretical perspective, right? And yeah, this is the fun part. Okay. So when you guys learn languages, you have to learn like different like characters or little things about nuances about the language, right? To make sense of it, the way things are written. Math is kind of the same thing. It's no different. So you have to understand the way things are written. So, and I just to throw it out there, I was a bit of a space cadet when I was in high school, so I didn't really pay attention to this until college. I'm like, oh wait, what is this? All this stuff. So hopefully you guys pay attention to this now because I don't want you guys to get confused. Like, wait, dur dx, what does that mean? Df dx, what does that mean? These are all the same thing. These are all the same thing. So we say, here's what we'll call it, but these are all the same, just so you know. Some of them, oh, you'll see. They're all the same. Just different ways of writing the derivative. That's it. They're all the same. Before I talk about it, we call this output the derivative of the function of f. So when you see this right here, that's the derivative. When you see that, that's actually kind of a more popular way of writing it. I like writing it that way. Here's what we say. F prime, the little accent symbol we call prime of x. So I say f prime of x, like f of x, you guys know that, right? Just you say f prime of x. So you add that word prime to indicate derivative. This right here, we call it y prime. This will probably be the more popular because it's easy to write. So if you have like y equals an equation and you want to find a derivative, you write y with the accent mark. That's popular. A lot of people like to do that. I personally like to do f prime of x because I want to show I'm plugging something into it afterwards, or it's a function of x. I like doing that. And again, before I get to the other three, if the limit or derivative exists, we say it's differentiable. I mean, you're able to differentiate, right? I'm just doing a play on words. Like if you're likable, you're able to be liked, right? Like you're likable, right? Because I said so in my honors card for you, right? So yeah, Yeah, just able to differentiate. So anything that's differentiable means you can find a derivative at every point in its domain. That's very important, by the way, because we're going to talk about continuity and differentiability. Not today, I think, but definitely tomorrow. Huge. We have to talk about the connection, difference between continuity. You remember that like task question, we had like the P and Q thing. We had like to make it continuous. We're gonna do something similar to that with differentiability. Yeah.
I don't get how like on the box, like how f prime of x can equal a limit. This is no limit, just a constant.
No, it could be a function too, because we could get an expression for that limit. So
Okay.
we could get expression also. Great question. Actually, I'm glad you brought that up. You're talking about this versus this. That's what you're talking about, right? So I'm gonna clear up right now for you. It's a fantastic question you brought up. This right here is a numerical value. Just so you get used to what I do. That's a numerical value of derivative. So whatever a is, like say a is like 5, then I want that slope, right? That's gonna be a slope. Or a slope, right? So that's a terrible looking S. Goodness. I'm still waiting for that stylus you guys get for my birthday like a few months ago. Don't you got that, didn't you?
I don't understand how you write like this on your iPad or on your.
Mouse.
I know, but with a stylus, like
Stylus?
it might be worse.
It could be. It all depends. No, you can just do it on the screen. No, you do on the screen itself.
I know, but
Well, I have to take my time. I yeah, I should. I know.
Like an iPad.
Where you write it.
Yeah, I know. Just old habits die hard. Yeah. Okay. And this right here is going to be a algebraic expression for the derivative. So hopefully that clears that up what that means. So f prime of x we expect to be an algebraic expression. F prime of a would be a numerical value. Okay. Let me talk about the last three notations. So you got f prime of x, y prime. Now this one here, and it's gonna be kind of funny the way I'm really gonna get incredibly phonetic here. D y over dx. So dy over dx. Why does that matter? That will won't get to until the second semester of calculus, which obviously I won't cover with you guys. That will be next year in AP calculus. Yeah, dy over dx. You want to be able to write that because you're gonna have to separate that eventually down the road. We won't do that in the first semester or what we cover in this class. But dy is kind of like delta y. It's kind of like change in y. Dx is kind of like delta x, like that change in x. So if you want to think of it like that, that's another way of writing it. Yeah, 100%. Yeah, and that would be like, for example, velocity is derivative of position, right? Or exorcist derivative of velocity, right? We do talk about that stuff in this class later on. We say dy over dx. And let me clear a screen for a moment. Let me move some stuff around. Okay. So now let me talk about the other ones here. This right here, we'll say df over dx. And lastly, this is kind of an important one too. We'll say d x of f of x. Yeah, I know. ddx of fx. ddx of fx. Okay, great question. Great question. So here's this is the part where I wasn't really present to when I was in high school because I just wasn't really paying close attention. That's my fault. So this right here is considered the derivative operator.
Why do we say dx instead of d over dx?
I don't know, actually. I don't know. But when you see this here, that's actually not an expression. That's a function. That's like an operation. So this is an operation that you apply to a function. This maybe that's why we don't do that. Maybe I don't know. Maybe that answers your question because it's not a function or expression. It's not something of or over. Oh, you can say d over. I'm not sure if I'm answering the question, but this is an operator we're applying to that function. So when you see this here, this means that hey, let's find the derivative of this guy. That's what it means. I mean, yes, these all mean the same thing, but this is a little more intentional. Like I want to take the derivative of something. We see d dx. This right here, you've done it now. It's like, oh, okay, the derivative f over x, over dx, right? So d dx, that's going to be an expression. Yes, exactly. Yes, exactly. The ddx, but the ddx of f of x is df over dx. Yeah, I know the same thing. They're all the same, but ddx on its own is an operator, just so you know. ddx on its own is an operator.
Will a function ever have two derivatives?
Oh yeah. Oh yeah, we'll do two. Oh yeah. Oh yeah, we'll do second derivatives also. That's acceleration, by the way. Yeah, which you probably learned in physics. So all right. So let's keep moving here. So let's just do it now. Okay, now
dd of x.
I've gone over all the semantics. Let's just do some work here. So find that. So really just doing this. The limit as h approaches 0 of x plus h cubed minus x cubed over h. In case you guys forgot, this expands like this. I think we did this actually the other day, right? We plug in a number, I think, right? I think we did this. Let's expand it and clean it up. We're okay with that so far? Yeah, no problem. And then cross stuff off. Any that does not have h, if you do this correctly, any that does not have h should go away because the intention is to factor out the h. If you factor out the h, you should get this. What happens to h's? Cancel, cancel. And at this point, you can just plug in 0 for h. And what do you get when you plug in 0 for h? 3x squared. Yep.
Isn't it x equals 5?
We'll get there. We're not there yet.
So
I said the first part.
You put a value for x, you just
No, the first
the
part was
equation.
asking for the equation. That was the first part of the problem. I haven't done the second part yet. There's two parts.
where does it say that? I thought it just says at that one point.
Find d over dx. part one. Yeah, sorry, it's not labeled as nicely. Sorry about that. Okay, then let's find the equation of the tangent line, which I know you guys can do. By the way, what's f of 5 going to be? If I plug 5 into my function, what do I get?
25.
125? Yep, good. So y minus 125.
Yeah, and 74.
X cubed.
No, the output slope is 75.
Oh, yeah.
Yeah, the slope is 75. Let me write that 125 a little better. No, I have to give the y coordinate that goes with it as well. That's the first thing I was saying. But you're right, the slope is 75. Plug into your yeah. Now the beauty about this is that now you can find the slope for any point on the curve, right? And this is now the graphical connection I want to make. This is very, very important, actually. How does y equals x cubed look? Like this, right? Ooh, I'd actually, it's probably the best x cube I've ever drawn in my life. It's a good one, huh? No? Is it good? It's good. Yeah, it's nice. Yeah, thank you. Thank you, Marcus. I think it's really good. Okay. The point, okay, I'll stop bragging myself. Okay. The point I'm trying to make is that if I draw a tangent line, right? Oh, is there a problem? What's
No.
oh, you're good? Okay. If I draw a tangent line, is my tangent line ever negative? This curve?
Use this.
No. It's always positive. In fact, actually, if x gets larger, does my slope gets more steep or less steep? More steep, yeah, right. Well, think about it. 3x squared. Can that ever be negative?
Cubed plus 3x.
No, that can never ever be negative. You're squaring
Square.
and multiply by a positive number. And if x gets bigger, does that number get larger? Yes. So 3x squared is being used to describe every slope on this curve. We are actually going to graph derivatives from an original graph. We're going to do that eventually. And it's actually a really cool, like, kind of game we play where you see if you can beat my score. Like, there's actually a website that actually checks your accuracy of how well you can sketch a derivative from an original graph, and see how accurate you get. We'll get there. I think maybe Friday. Actually, tomorrow we might get to that. I don't know if we'll. I think we do get to that. But to actually take a look at how the derivative expression relates graphically, right? All those slopes will all be positive. 3x squared confirms that. Lydia. You mean like a piecewise function? Yeah. We're not there yet. We'll talk about that because that's when we have lack of differentiability. I think we do that tomorrow. Not really, no, because if we have continuous functions, no. I mean, okay, if you have a discontinuity, okay, let me take it back. This is all tomorrow, actually. This is good. So like we have y equals 1 over x, right? Y equals 1 over x has a discontinuity of x equals 0, or infinite discontinuity. So you have two branches. Each of those branches have their own kind of thing, right? As you would kind of imagine, because so we'll talk about that when we get there. But which by the way, that derivative will be negative 1 over x squared, and it has a kind of its own shape. But yes, sometimes you do that expression would still be true. Let's talk about it tomorrow because I can get really we could get really theoretical about this. But great question. But for now, let's focus on continuous functions. You get one expression that represents the derivative. Okay, let's do this again. Why don't you guys try this on your own? Actually, speaking of devil, I did talk about 1 over x, right? Here we go. I already gave you the answer. I know what the answer is. The answer is negative 1 over x squared. And by the way, there is a shortcut for doing this. You guys will get incredibly upset at me next Tuesday when I show you the shortcut. They're like, wait, why do we do it this way? You probably could look it up online. You can talk to a friend who took this class or just in calculus. There are shortcuts that does this derivative like that really fast. But for now, we're doing it this way. So just deal with it. So you want to find f prime of x, and yet another way of writing the derivative, f prime of x, limit as h approaches 0. Excuse me. Lose my voice here. So what do you think our algebraic technique's going to be? We should do what? Find the LCD. Yeah, what's your LCD here? 100%. Let's do it. Now, one way you could get a little creative when dealing with complex fractions, instead of literally combining the top two fractions up top, I could opt to actually, what I like to call bust the fractions right away. You're right.
Bust the fractions.
Yeah, just get rid of it right away. I know.
Alright.
Yes, this is a term I used when I taught algebra 2 trig honors many years ago. And hold on. Here we go. There we go. Yeah, that's like bust it. Like kind of like that song, the rap song from the 90s.
Got you.
Okay. Okay. Yeah. I'm a child of the 80s and 90s. So you distribute it, you get this. F prime of x. And see now the fractions are busted, right? Because what happens when you multiply this by this? The x plus h's go away, right? To get x. How about the other guy? But put parentheses. Put parentheses. Very important. Put parentheses. And what happens to the x's up top?
They'll cancel.
Oh, and I was getting lazy.
I was gonna say, they're new.
Getting a little lazy. Yeah, minus 2 points for me. Negative h. A lot of writing, I know. H's cancel. You get negative 1 over x squared. Because when you plug in 0 for h after you cancel out these h's, you can plug in 0 for h right away.
Like matter what? Like I got -1 over a squared. Does it really matter? Like what variable you use?
Yeah, so that's arbitrary, right? 100%. Fully arbitrary. So negative 1 over x squared. Okay. Okay, now let's investigate this graphically. Remember we talked about at the start of the year, like what's increasing, what's decreasing. You know, I think I gave you guys a question where you had to like investigate a function in a lot of different ways.
How do you the h and increase?
Oh yeah, I plugged in 0 after these went away. I plugged in 0 for h. I skipped a step. No, there's the intermediate step I skipped. You could write it out and then show that you're actually plugging 0 afterwards, right? Okay, 1 over x, right? Is this an increase or a decrease in function, guys?
Decrease.
Yeah, it's decreasing the whole time. As x gets larger, y keeps going down. And of course, there's a break in the graph. This is purely a decreasing function. Think about it. Any slope I draw is going to be negative. Look at my derivative. Can negative 1 over x squared ever be positive?
Whoa.
No. 100% of the time it's always negative. So this makes sense. And in general, it's just going to be kind of have a squaring nature to it, I guess. Like if I were to find a slope over here at 1, of course it's -1, but if I do a slope at 2, it actually is going to be -1/4, right? Slope at 2 is -1/4. Or if I do a slope at, say, 1/2, x equals 1/2. What's my slope at 1/2? -4, right? And as x gets closer and closer to 0, what's happening to my slopes here? They start going towards infinity. What's going to slope eventually when I get close to 0? Does not exist, or negative infinity. Hence, it's not differentiable. This is all stuff we'll talk about tomorrow. Because you can start looking at, that's why it's called infinite discontinuity, guys. Because what's happening to your slopes as you get closer and closer to 0? They start to become more infinite. That's where that name comes from. It comes from that. So, yes, everything become more enlightened with calculus. It's a great class. Love teaching. All right, let's try this next one here. And then we're going to talk. Actually, we are going to talk about graphs a little bit. Okay, we'll get there. Okay. Why don't you guys try this one on your own really fast, and I'll do some summaries. And I'm going to talk about sketching the graph.
How did you cancel it? Isn't it minus x squared?
For the root of x is multiplied, so just percentage.
Minus x, yeah.
You're starting this way, right? Start that way. And you should be doing this next, right? And if you FOIL it correctly, you should get x plus h. We're dealing with difference of squares, so things will cancel. So the outside and inside terms should cancel when you do the FOIL process if you do that correctly. So you guys should be aware of that. And it's gonna look kind of like this, I think. You should get that
Is
next.
the power that it's going to always gonna be what it's like multiplying by?
Yes, it will. That's called that's true for any power type of term or a monomial. Yes, it will. That's called the power rule. Yeah, it will. That's a good observation. Yep, it will. That's a shortcut rule. See how those go away? What else goes away, guys? It's actually, let's just do it this way. So you're stuck with
H.
h up top. So you have h over h over. Sorry, no, over. Two h's. Those h's clearly go away. And then if you plug in 0 for sorry, 0 for h, you should get 1 over 2 root x. So the starburst there, put 1 over 2 root x.
What is the starburst?
That's just the thing here. It's called starburst.
Oh, so you're gonna give a starburst?
I like candy.
Yeah.
Sure, why not?
That's what I was thinking.
Yeah, I think so. Okay.
Give me 2x.
Yeah, it will be. Or x could be 3x squared, right? So you start. So we see here that's 2x. That's just m. That's from the previous notes. We noticed that. And that makes sense, right? Because for a line, what's the slope of a line? M, and the slope of the tangent would be the line itself, right? X squared, isn't the slope negative when x is less than 0?
Mhm.
Is the slope positive when x is greater than 0? Is the slope 0 at 0?
Zero.
Yeah, right. So 2x makes sense. Yeah, so we start seeing this happen often. Oh, by 1 over 2 root x. If you graph root x, are the slopes ever negative for that curve? No. They're always going to be positive. So 1 over 2 root x is always positive, but it's going to be kind of a smaller slope in a way. And also another thing we're going to talk about is concave. Actually, I don't know if we'll get to this term, but there's another term called concavity. It's how the derivative changes. So you look at the rate of change of a rate of change. That's like a second derivative. I don't know if we'll get to that. Yeah, which is kind of like acceleration. All right, so now let's move on to graphs. Okay, so here is f of x. Here's f prime of x. So I did say we're going to graph this on Friday. Well, we're going to do some of it today. How do I sketch graph of f prime? Now, fortunately, these are all linear parts. Let's find the slope of each part. So f prime of x is simply slope, right? We know this, right? What's the slope of the first portion? What would you say the slope of that first portion is going to be?
Negative.
Probably -2. How about the slope of that second portion? 1. How about the slope of the flat line? Yeah, see, that's a slope of 0. Correct. How about the next one? And the next one? Probably
3.
Probably 3. Yeah, we'll say 3. Yeah. Okay. So how do you graph this? You graph it like this. Okay. One thing that I want to point attention to. We'll talk about this tomorrow, but just so you guys know right now, sharp corners are not differentiable. So you cannot find a derivatives at sharp corners. So we have to put like holes in place of them. So or we say the derivative at sharp corners, D&E, exactly, does not exist. The derivative sharp corners just don't exist. We're gonna take a look. So you know how we did left and right hand limits? We're doing left right hand derivatives, and you'll discover that the left right hand derivatives don't equal each other at certain points, and we're gonna have that discussion on Friday. So, but yeah, sharp corners are not differentiable.
What's a slope equals something infinity?
That's a 0. Yeah, sorry. I was just copying what I had in the table. That's all. Slope equals 0. Yeah. Yep. Okay. Let's try this again. So let's give the x values at each of these 7 points. Oh, that's a g, by the way, right here. So the x value A is -4. The x value B is -3. Then -2. Then 0. Then 2. Then 3. Then 4. You agree with that so far? The x values. Okay, the slopes. You really should like try to use like a ruler or I don't know. We're just
Make
gonna
it very easy.
we're just gonna estimate it. What would you say the slope is? If I drew a slope at A, if I drew a tangent at A, what would you say the slope would be about? About 3, let's say. So these are estimates, just so you know. Those are just estimates. What would you say the slope would be at B? Would it be it's gotta be less than 3, obviously, right? All right, probably we'll say 1. You want to say 1.5?
No, I think one.
Okay. How's C?
Yeah.
And by the way, is that a peak? It is. How about at E?
Relative peak.
It'd be probably E. Sorry, let's do E right now. Yeah, notice how highs and lows have slopes of 0. That's going to play a key role in finding high points, low points. So, when you have to graph like polynomials accurately, and you kind of had to kind of guess where the highs and lows were, now you'll know because of the derivative. When the derivative is 0, that's going to be highs and lows, right? Or where the curve might flatten out. What do you say D is about -1?
Yeah.
At F, probably back to 1. At G, probably 2, we'll say. So what I'm going to do is I'm going to plot these points. So this is now a derivative graph. That's a derivative graph. And what's going to happen is that the y coordinates represent the slope. Yes. Represent the slope of tangent lines of f of x. So -4 comma 3, -3 comma 1, -2 comma 0, 0 comma -1, 2 comma 0. What do you think I'm plotting?
Parabola.
Yeah. Looks like I'm graphing a parabola, huh? Why would that make sense?
Because like the derivative of whatever this
Yeah, how
graph
many
is
how many
pi
x intercepts
squared.
does this curve have right now? The original.
3.
No, the original, sorry. The original curve. Yeah.
3.
3. And the end behavior is odd, right? It has odd end,
Right.
yeah, right? So it's probably cubic. And we saw we had x cubed, the derivative was like something with x squared, right? So this looks quadratic, right? So we're feeling pretty good about this. This makes starting to make a lot of sense now. Because we saw when we had a cubic function, the derivative was quadratic, and we're kind of see the same thing here graphically, right? And remember, this is very important. The y coordinates on the derivative graph, I cannot emphasize this anymore. The y coordinates of the derivative graph, they represent slopes of the tangent lines of the original graph. Okay, very important that we see that.
So like we're gonna need to find that many slopes. I mean, I seen
Yes and no. Here, let's see if this works. Here, I'm gonna see if this GeoGebra. Oh, there we go. Yes, got it right here. Yes, okay. This is what I was gonna talk to you guys about really quick. We'll play this game on Friday afternoon. And if you guys want to practice, I can put in Schoology, see if you can beat my score. And my career is really slow, so not sure. Okay, so let's reset the graph. Okay, so here's what's happening. The curve that's dark, that's not blue, that doesn't have dots, that's the original graph. Okay, so this is f prime of x. So that's fx. Sorry, my bad. The dotted curve is f prime of x. My goal is to sketch a derivative. So you guys can help me out. See if I should. So right now at -6, is my slope negative or positive?
negative.
Probably about -2, I'd say. So I'm gonna put that around -2. Look at -5. That slope's still probably about -2, right? Maybe it's getting a little less steep. Look at -4. That slope's probably about -1. Look at -3. That's probably a slope of about 0. Probably still slightly negative. Look at -2. It's still positive or negative now.
Positive.
Yeah, probably 1. Here, probably about the same. At 0, probably still about positive. And that's not looking too hot, but that's okay.
Yeah, it doesn't look good at all.
Yeah, it kind of looks sloppy. Yeah, I'm probably not gonna score very well here, but it's getting less steep now, right? Okay. Yeah, this is kind of a crappy graph, actually. That's a little better. I did have a mouse, so I'm kind of cheating a little bit. Yeah, then at 2 is probably coming back down again. And it's probably negative over here. Probably negative, negative, and definitely negative.
All right, see what you got.
Right.
Oh,
81%. All right. There are the results. Okay.
What's your score?
Oh, I could get 90, high 90s. That's just I'm a little rusty right now.
Oh, that's all it is.
Yeah. So we'll do a little competition on tomorrow afternoon. And if anyone could beat me, I could let you guys watch March Madness tomorrow. We'll see. If any games are close, we could put it on. All right. Lunch. I can't wait for lunchtime. It's gonna be so much fun when all the games are going on.
Yeah, that is fun.
That's fun. All right. Anyway, so what can you say? Actually, let me put the graph back. Okay. So shoot, darn it. Let me reposition this.
Notes are kind of feeling long.
Well, the notes.
Feel long.
Oh, I know. 100%.
Do we gotta get the test back too? See that?
Maybe.
Oh, maybe.
No, I'm gonna pass by. Don't worry. I got you. All right. Anyway, so oh man, hold on. Here we go. Let's try that again. Much better. Here we go. Okay, so what can you say about the y values of the graph f prime when f are increasing? The y values are positive. What can you say about the y values in the graph f prime when the y values of f are decreasing? That's negative, because that's going to be when f prime is positive here, and that's when f prime is negative here, right? And what can you say about the f prime when it has a horizontal tangent? 0, exactly, right? Exactly. That's what's happening. So let's do one more kind of thing here. I think I'll stop after page 4 because I'm gonna I can pick this up again because I don't want to really rush this. So let's just do this example 6. I can speed this up. With you guys on Friday. So if we look over here at where would have a slope of -3 on this graph? F for sure, right? Where would a slope of -1 would you say? Yeah. Where would slope be 0? Where would slope be half? Yeah. Where would slope be 1? Probably B. And which one's looks like the steepest? Probably D. Yeah, I'd agree.
Sounds good.
Yeah, so we'll do this rest of this, and then just kind of a, yeah, there's no way I'm gonna get through all this on Friday. I'll probably, yeah, I think we'll get to the middle of page 4. Yeah, I think we'll be, or middle of page, yeah. Yeah, I think I know how I want to pace this tomorrow. We're good. All right, so we'll just stop there for today. Homework is going to be, oh, sorry, hold on. Homework's going to be this. Sorry, I'm gonna sign homework on if you're watching March Madness tonight. But it's gonna be yeah, just 1 through 6. Yeah, so right here, where it says handout B, 3.1. Just 1 through 6. I think you guys could totally handle that. Yeah. I think that's fair. So